Good morning everyone, and welcome to today's worked exam answer video on my bizarrely creased piece of paper, so apologies for that. Today I've chosen to have a look at an esters question, which, as with yesterday's amines question, covers a variety of different things. So initially we're looking at how we can prepare an ester via two different methods, using either an acid anhydride, for which we have to write an equation and name the ester produced in that way, or we can use method 2, which involves an acyl chloride, and we then have to outline the mechanism for that method of preparation. Turning over onto the back, we're then looking at the ester shown, which is present in vegetable oils. We're looking at how we can hydrolyze that to form soap, and then we're also linking that to the formation of biodiesel. So as always, I will highlight and annotate, and then I will come back to you with my worked answers very shortly. Okay, so there's a few things that I think it's been really helpful for me to do as I've just been highlighting, annotating and writing out my model answers, is for the first part of this question and for the hydrolysis of the ester on the back, I've tried to use the different colours of the different pens to show where the various atoms are going to in the products. Hopefully it will be clear, but as always, if it's not, please do ask. So we're told that esters are used as raw materials in the production of soaps and biodiesel. A student prepared an ester by two different methods, so we can use an alcohol with an acid anhydride or an alcohol with an acyl chloride. You get the same main product, you get different secondary products. It will be a carboxylic acid with an acid anhydride, as you'll see, and it will be hydrochloric acid, or hydrogen chloride gas rather, with an acyl chloride. That's because of the different functional groups of the acid anhydride and the acyl chloride. We don't need to know how to do the nucleophilic addition elimination mechanism with the acid anhydride, but we do with the acyl chloride, which is why part II is asking you to do the mechanism for nucleophilic addition elimination, because that's for method 2 using the acyl chloride. However, in part 1, we're only asked to write an equation for the reaction between the alcohol and the acid anhydride. We do also have to name the ester as well, which I've just noticed that I failed to do. So I will pause the video now, add that name on, and come back to you and continue that train of thought. My apologies about that, but a very good learning tip on exam technique. You should always just go back and double check that you have answered everything that the question is asking you to do. So I had written the equation, I'd then carried on and forgotten that I needed to name the ester as well. So just always double check you've answered everything that is required of you. Now, I thought it would be helpful to draw out the structure of the alcohol, because the way that they've written it is a little bit weird. It's a secondary alcohol. So they've gathered the CH3 on the left and the right, and that carbon with the H and the OH is the middle carbon. Looks very odd, so I thought it'd be helpful to have that drawn out. And then I've also shown the structure of the acid anhydride, because again, structurally it looks a little bit weird. But what this is trying to show, the O outside of the brackets is this middle O here, and then we can see above and below that we have the same fragment of the structure, the CH3CO. That's therefore in the brackets, and because we've got it twice, both above that O and below, we've got the 2 outside, and then we've got that O there. So when we react an acid anhydride, we are either breaking the bond there between the C and the single bond O, or that bond there between the C and the single bond O. And it doesn't matter which one we do, one of the fragments will have the extra O. That will always go into the formation of the second product, which is our carboxylic acid. The one without the extra oxygen is going to go into making, in this case, our ester, and we're making an ester because our nucleophile is an alcohol. So like I said, fragment of the acid anhydride without the extra O is then going to react with the nucleophile. The O will lose its hydrogen, as we'll see in the mechanism in a second, and that O with the CH and then the CH3 twice, that then gives us our ester functional group, because we have the CH3CO from the acid anhydride, and then we have the OCH-CH3 twice from the alcohol. That makes our ester. And then the second CH3CO with the extra O and the H from the nucleophile give us our carboxylic acid as our byproduct. Now this is a very weird ester. The part after the single bond O, rather than having all of those 3 carbons in a line, because the oxygen was on the middle carbon of our alcohol, we've got a longest chain of 2, and then we have a methyl group. So it's not propyl-ethanoate, and if you need to draw the structure of the ester out, do so before naming it. It would actually be methyl ethyl ethanoate. So ethan because the 2 carbons there, O8 because it's an ester, and then here, if you draw it out, if you can't see it, we've got the methyl ethyl part of the ester. The same ester is made whether we use an acid anhydride or an acyl chloride. So it comes down to a couple of things like cost, byproduct, speed of reaction, as to whether we would choose to use an acyl chloride or an acid anhydride. When we're outlining the mechanism for the reaction of the acyl chloride with the alcohol, it will be nucleophilic addition elimination. We have not been asked to name it, just outline it, but that is what it is. So in the first step, we're using the lone pair on the oxygen from the alcohol to attack the delta positive carbon of the C double bond O, and one of those bonds between the C double bond O will break with the electrons going to oxygen. That's the addition step. Then in part 2, we do the elimination step. So we reform the C double bond O, which we have to form our ester product. The carbon-chlorine bond breaks and the chlorine gets eliminated, hence addition elimination. And then the O from the alcohol is now forming too many bonds. So we have to return some electrons to the oxygen so it gets one of its lone pairs back, and the H will then come off as a H+, and that gives us HCl as our byproduct instead of the carboxylic acid that we would make with an acid anhydride. There is no need for us to draw the product of this, not least because we've already identified what the product is in the first part of this question, but there is only one possible product it could be. And if you draw the product and you draw it wrong, you will lose some of your marks for outlining this mechanism. So my advice is to not do it, but if you do it, please just be very careful. So those are the different ways that we can prepare the ester in the first place. And now I'm going to turn over and we'll have a look at the soaps and biodiesel component of this question. Okie dokie, so they've shown us an ester and said that it occurs in vegetable oils. Now this is a triester because we have 3 ester functional groups in here. We've got the C double bond O there, the C double bond O there, the C double bond O there. And that's because the alcohol that we've used to make this particular ester is glycerol. And glycerol is an alcohol with 3 OH groups. Glycerol is potentially a more biological name for it. If we were naming it using the chemistry IUPAC rules, we would name it propane 1,2,3 triol. So 3 alcohol groups, which means that we can use 3 carboxylic acid chains to get those 3 different esters. So because it's made from glycerol, it might also be called a triglyceride. As a chemist, I prefer to call it a triester. Same thing. It doesn't matter what you choose to call it. Now, we can hydrolyze esters, which means that we can break them back down again into their components, and we can do that using either an acid or an alkali. And they've asked us to use sodium hydroxide. So that is a clue that we're going to get alkaline hydrolysis, and they've said that we're going to form a soap. Now, saponification is the name of this specific reaction where we do alkaline hydrolysis to make soaps, and the soaps needs to have chains of carbons around 16 to 18. So we've got the 17 carbons, and then we've got the carbon of our ester group to make 18. So they would then be our soaps. Now, if we were to do acid hydrolysis, we would do the complete opposite reaction of how the ester was formed in the first place, potentially between a carboxylic acid and an alcohol. So that's the third way that we can make an ester, in addition to the 2 we've seen on the other side of this question. If we were to then hydrolyze it using an alkali, rather than getting back to the original alcohol and carboxylic acid, we do still get the original alcohol, but we get the salt of the carboxylic acid instead, which is this, and it is the salt of the carboxylic acid, which is our soap. So if we want to hydrolyse this ester, it's the bond between the carbon and the single bond oxygen that will break, which I've tried to show with that ziggy-zaggy yellow line. Again, with the colours, I've tried to show that on the left-hand side of the yellow pen line, we've got the start of our glycerol molecule, which is the alcohol, and we need to obviously get some hydrogens to reform those OH groups. The rest of the chains are then going to become our carboxylic acid salts, and I've written them the other way around just because I think it's easier to see the functional groups this way. So we're using sodium hydroxide. The reason we need 3 sodium hydroxides is because we've got the triester. We need the 3 H's from the NaOH to go onto the O's from the glycerol. And then we're going to use the ONAs from those 3 sodium hydroxides to give us the salts of those 3 carboxylic acids. Now I've had to write them separately because the chains for each strand of the triester have a different number of hydrogen atoms. If they didn't, I could have just written it once and again balanced it with a number 3, but because we have got different lengths changed, I've had to write them all out separately. So those would be my soaps, and there is my glycerol. Then it's talking about biodiesel. So biodiesel is a mixture of methyl esters, and we have to give the formula of the biodiesel molecule with the highest MR that can be produced by reaction of this ester with methanol. Now, the production of biodiesel is a transesterification reaction, so we don't want to have the glycerol alcohol on there anymore, so we replace it with methanol, and that's why the esters are all methyl esters, because the alcohol component always comes after the single bond O. We always name that first when we name our ester, so it'll be methyl whatever it might be. So to get the one with the highest MR, we just need to look at the lengths of these 3 chains. They've all got 17 carbons, but the middle strand has the 33 hydrogens, so that's the one we're going to use. Then, like I say, we need to get rid of the glycerol part, add the CH3 from the methanol, and then that would be the formula of the biodiesel molecule with the highest MR. We would also get C17H31 COOCH3 and C17H29 COOCH3, but of course it's asked us for the one with the highest MR, not all of them, but them 3 would then be a mixture of methyl esters, which would be our biodiesel. Hopefully all of that's been useful, particularly with the colour coding. If anybody is unclear, however, please do let me know. And if anybody would like a scanned electronic copy of this final workings so that you've got that colour coding, please just leave a comment on the video and I can ask for your email and send that over that way. Thanks so much for watching, guys. Hopefully you found it helpful, and I wish you a very lovely day.